Next up is entropy and trying to get a handle on what we mean by entropy. Since our microstates are products of those microstates of the two systems, we can use logs to turn it into, instead of products, turn it into sums. And we can rewrite this quantity, this energy quantity tau, as 1 over tau is a derivative with respect to the partial derivative with respect to energy, the log of the number of microstates. Well, we're going to define entropy, S, as simply S is the Boltzmann constant times the log of the number of microstates. Now, if we do that, then one of the things we get out of this, we already know that, well, we'll get there, right? One of the things we get out of this is that we can raise both sides of this to E, and we get the number of microstates is the entropy divided by the Boltzmann constant. So now we've got this partial. So let's take the partial of the entropy with respect to the energy, keeping all other variables constant. Well, we get Kb over tau, which is 1 over the temperature, right? So Kb times the partial of this, I already know the partial of that is 1 over tau. And so we get 1 over the temperature. So the partial of entropy with respect to energy is 1 over the temperature. Other properties of entropy, the entropy of the two sides sum, while the microstates multiplied, because entropy is related to the log of the microstates, the entropy sum. And finally, if the other variables are fixed, number of particles, volume, etc., then we can take this and call it a derivative, ds equals dq dt, and not use the partial, right? Because we're using, the only thing that's changing is the heat, so ds equals dq over t. Now, one of the things to be careful with in using any of the equations in thermodynamics is many of them you'll want to grab, but they will have these caveats. Keeping the other variables fixed, we have this expression. Now, eventually we'll get to a more complete expression for this that doesn't have anything fixed, and you'll see what that is, but later in the slides. But just keep in mind, when you start to grab something, you have to understand the conditions under which it applies. The Boltzmann factor, or density of states factor, is the ratio of the energies in two different states. So you got a number of states of energy US, number of states at energy UR. The ratio of those two is the Boltzmann factor. And so when we look at the probability ratio between the two energies, we end up with this result, which is the probability ratio of the two different energies is the Boltzmann factor, e to the minus the difference in energies over kBt. So this gets us to our Boltzmann factor we're going to use here and there throughout the problems. And that Boltzmann factor leads very quickly into another bit we'll use very often, the Nernst equation. All right, the probability of finding an ion on one side of a membrane versus the other is simply the ratio of the concentrations on the two sides. That kind of makes sense, doesn't it? You know, you got concentration on one side that's twice as high as the concentration on the other side. The probability of finding something is going to be proportional to the concentrations. So the ratio of the concentrations is the ratio of the probabilities. If we stick this into the Boltzmann factor, we get the ratio of the concentrations is the ratio of the microstates, right? E to the minus difference of energy over kBt. And the factor in brackets is 1. So the ratio of concentrations ends up being e to the minus delta U over kBt. The energy difference has many different factors, right? Many different factors, some of which are the same, like kinetic energy versus potential energy. All right, we got kinetics, we got potentials. But this gets us to rewriting this differently in that in this one, the kinetic energy drops out, and we've got C2 over C1. Why does the kinetic energy drop out? You're going to ask, because we're at constant temperature. where thermal equilibrium, temperature is the same everywhere. That means kinetic energy of everything is the same. So this gets us to the concentrations, the ratio of the concentrations of ions on one side of a membrane versus the other is given by e to the minus z, which is z is how ionized they are. Is it +1, +2, +3, -1, -2, -3? E is the charge on the electron. V2 is V2 is the electric potential on side 2. V1 is the electrical potential on side 1, right? And so the concentrations depend on the difference in the electrical potentials across a membrane and the temperature and the Boltzmann factor and how ionized they are and what does this say about the concentrations, right? Start playing around with what if Z is positive and V2 minus V1 is positive, then this concentration on side C2 is going to be less than side C1. If, on the other hand, Z is negative and V2 is greater than V1, then C2 is going to be greater than C1. And so you can see the voltage bias across the membrane is going to drive the concentration at equilibrium one direction or the other. If we take a logarithm of both sides of that, we get a new little expression that we can arrange, and we can get to the change in electrical potential from one side to the other is the Boltzmann constant times the temperature times the temperature divided by the ionization factor 1, 2, 3, -1, -2, -3 times the charge on the electron times the log of the concentrations. And if we multiply the Boltzmann factor by Avogadro's number, right, the Boltzmann constant by Avogadro's number, we get the gas constant R, and we can multiply E by Avogadro's number, and we get Faraday's constant F, and we can express this Nernst equation as in the voltage across the membrane is RT over ZF times log of the concentrations. RT over F is a constant. It's 26.7 millivolts. So our 26.7 millivolts divided by the level of ionization onto the log of the concentrations. Now, one thing you should note when you go to use this, we absorbed a minus sign in the log at one point, and so instead of being minus log C2 over C1, we have plus log C1 over C2. This is very useful for looking at the concentration on various sides of a membrane based on a potential across that membrane. And this is going to be applied throughout our the physics of the body and cells and nerves and everything else as we go through the rest of the book. All right, that's it for the Nernst equation.